This conference will now be recorded.
Very good evening, students. Today we are starting discussions on magnetism. In fact, the chapter numbers will be 4 and 5, not 3, 4. It will be 4 and 5 because we will see magnetic effect of current as well as the magnetism chapters. Various questions which are asked in JEE Mains. Excuse me. This will be chapter number 4 and 5. So we'll discuss various numerical problems on magnetic forces, Lorentz forces, Biot-Savart law, Ampere's circuital law. There should be Ampere's circuital law. And their applications, galvanometer, etc. And along with, so let us see. So in the magnetism chapter, in the first chapter, these things are there, like fourth chapter, magnetic effect of current. Basically, there are many problems from this first chapter, fourth chapter itself. We'll first discuss, and in between some questions may be coming from chapter 5th also, so we'll discuss together. So in this first question, let us concentrate the statement first. The question is, a positively charged particle, okay, I'll draw it. A positively charged particle moving in xy plane along x-axis, say this is xy plane, this is x direction, and this is y direction. So this is the charged particle. So there is a positively charged particle which is moving in this direction along x-axis. So there is a sudden change in its path due to the presence of electric and or magnetic fields beyond P. Suppose this is a point P. This is a point P. According to the question, the charged particle after P. So this is suppose a P point, and after P point, the charged particle actually is moving along some curved path like this. Curved path like this. Okay, according to the given figure in the question. I have forgotten to attach it here, so that's why I have drawn here. So beyond P there is electric field or magnetic field, or maybe both. Either electric field or magnetic field, or electric and magnetic field both are present beyond this point P. The curved path is shown in the xy plane. So this curved path is in the xy plane, is found to be non-circular. You have to see that this is not non-circular. Which of the following combinations is possible? Combinations of what? Combinations of fields, as you can see from here. This is equal to 0, first option, and B is equal to this Bj Ck cap. Similarly, other options are there given. You have to find out among these 4 options, one option you have to find out which will actually deflect the charge particle in this kind of non-circular curved path. So non-circular curved path we know from Lorentz force. We know from Lorentz force. What is Lorentz force? When a charge particle moves through a region where electric and magnetic field both, then the charge particle will experience a force FL, Lorentz force, which is given by Q into E plus V cross B. V is the velocity and B is the magnetic field. B is the magnetic field. So that is the, and if you analyze this product, you will be able to get the force, like magnitude of the force experienced by this charge particle beyond P, and also the direction. In fact, I'll just try to give you some glimpse or some idea what happens for, like what is the force experienced by a charged particle when it is passing through electric field. Suppose there is electric field like in this way, then if the charged particle is positive, suppose this is the direction of electric field, then this particular charged particle will experience a force along this direction itself. So that force can be written as FQ, electric field, or FE, that force, electric force, will be along the direction of field, along the direction of field itself. Okay, along the direction of electric field itself. Now, magnetic force FV is Q into V cross B. V is the velocity of the charged particle and B is the magnetic field. Now see, this is a cross product. So you have to apply the right hand thumb rule or right hand screw rule, whatever rule you know. According to that, you have to find out the direction of this cross product. Now look, if I take arbitrarily the angle between magnetic field and the velocity vector 0, that means 0 or 180 degree. If they are parallel or anti-parallel, then the force will be 0. Right? So magnitude of the force will be 0. Now if V, the velocity of the particle, charge particle, is perpendicular to the direction of the magnetic field, then this force will be the maximum force it will be. Okay, that is the magnitude, but what is the direction? The direction in this case, you know, like you have to find out, as I said, from the right hand screw rule or right hand thumb rule. So magnetic field, like this force, magnetic force, in this case will try to, when the field is perpendicular to the magnetic field, then the field, magnetic field, or the force, magnetic force, will try to exert a force to the charged particle such that its path will be a circle or circular path. So when the magnetic field and the velocity vector are perpendicular to each other, you will get circular path for the charged particle. Circular trajectory, it is said, it is circular when perfectly 90 degree. But suppose velocity vector has a component along the direction of the motion of the, sorry, B vector. If suppose B vector has a component along the direction, here it is supposed V is along this way. So if this magnetic field vector has a component along this direction, or there is electric field along this direction, along x direction, then it will not be a circular path. It will be actually spiral like this. Okay, and in fact, in this case, this is not a circular curve. It is actually spiral curve. So we can see there are two conditions for having non-circular path, as I have discussed. Either electric field has to be directed along the direction of the charge particle, or here in this case along the x-axis, or magnetic field should have a component. Magnetic field should have a component along this x direction. If magnetic field has component yz direction, let us see what happens in that case. So let us examine the options. So first option is equal to 0. That means the charge particle is moving under magnetic field. If it is the case, then only for the first case, and even in case of C, first option and option C, option A and option C, they will be, see, the charge particle will have only magnetic force. Let us calculate the magnetic force. In this case, suppose the velocity here v cross b, it is along I cap direction, and b is given. The first option b j cap plus c k cap. So the cross product I cross j will be 90 degree. So I and j, they are 90 degree. So you will have some value vb ij, and according to cyclic rule, it will give k. And again ik will give you minus vc, and ik will give you minus j direction. Okay, this is the circular. See, you can see there are actually two components in the magnetic force. One is along positive z direction, another is along negative y direction. If we say negative y direction, so this direction is actually negative y direction, as you see. But in this case, you look, there are component, like there is a component along k direction also. That's why this will not be a true option. Okay, that means if again this path is not a circular path, it is a spherical this is a helical path. That's why E is equal to 0 condition is not ideal case. Okay, so this, in case of C, if you just take cross product b I cap and this here cj, right, cj, here also it is j and component j and b. So cj, let me write here itself. Cj plus b k cap. Okay, so ij means k cap, so b c k cap. Ik means again ijk, so ik means it is minus j, vb minus j, vb minus j. Here also you look, there is a component along k cap direction. So that's why this curve path will not be obtained by these two forces. Okay, these two magnetic forces. That means this C and A, these options are not correct. Okay, I hope you have understood why not correct, because they have force component. Here only, in these two cases only magnetic force is responsible for this curve path, but we have seen that this curve path doesn't have only minus j component, it has k component also. So this is not the direction it should have. Okay, if only magnetic field is there, electric field not there, then we'll examine the option B and option D. Let us first see what is option D saying. Then we will go to the option B. What is option D saying? See, D has electric field along I cap direction, and it has B magnetic field along K and J cap direction. So first of all, V cross B, let us see. This is Bj. So in this case, see cross product if we take here I K, that means there will be a positive J cap component. Okay, positive J cap component, but here we should have only negative component, negative J cap component. Okay, so that's why we can just neglect this also. Okay, so the option D is also not correct. Now let us see option number B. Now see, according to this formula, if you find out magnetic force due to this, what we get? AB magnetic force. AB is equal to V cross B, so V I cap and B C K cap plus A I cap. So B C I K I J K, I K means minus J cap. Okay, I and I, if you take the cross product, if it is I, B it is I, so there will be no component in any other direction. It will have only minus J component. Look, now you may think that what about this electric field? This is also there. Yes, electric field is actually along I cap direction, that means along positive x direction itself. And in the beginning we have seen that the positively charged particle will be experiencing force along the direction of electric field. So look, this magnetic force is making the charged particle to move in this, like it has a tendency to make a circular path in this direction, y direction, negative y direction. Again look, again this electric field also at the same time pushing forward in the along the x direction. So that's how the path will be actually a spiral. Okay, and it will not be a circular shaped trajectory. That's why it is called non-circular in the beginning itself. So which of the following combinations is possible? So we have seen all the combinations. Only this combination matches well. Okay, so this will be the correct answer. So B will be the correct answer for this question. Now we'll see this question. This is also very interesting question. Same mistake is there here also. Okay, I'll next slides I'll correct it. So a conducting loop carrying a current I, you can see this is a conducting loop carrying a current I, is placed in a uniform magnetic field pointing into the plane of the paper as shown in the figure. So this is the magnetic field when it is assigned like this, so it is actually into the plane of the paper. It means the magnetic field is getting into the plane of the paper. Okay, now see, the question is the loop will have a tendency to contract, expand, move towards positive x-axis, move towards negative x-axis, or what? So in this case we have to see when a current carrying loop is kept in a magnetic field. Okay, suppose this is a magnetic field and a current carrying wire is going like this, an angle between them is theta. This is I, this is B. So in such case, this is current carrying wire. It is current carrying wire. It is carrying a current through it is I, constant current, and suppose it is placed in a magnetic field B. Then the direction of forces will be, or let us say what is the force. So in this case, the force will be magnetic force on a current carrying conductor is given by I dl cross B. B is a constant quantity. This is the force. Okay, a current carrying conductor can experience. Okay, so now look here. In this case, magnetic field is down, vertically downward. Okay, now if you apply uh, right hand thumb rule for this dl cross B, suppose this is a dl and its direction, you can see that the direction of the element is given, and also the magnetic field direction is into the plane of the paper. So if you apply right hand thumb rule, so at this particular portion the force will be along this direction. Okay, similarly the force at this position will be in this way, here also will be in this way, and here also it will be there. So in each case, if you see the direction of the magnetic force on the current carrying conductor will be always outward, radially outward. So radially outward. That's why this option will be the correct answer. The wire will be expanded. Okay. The wire will expand. So that's the reason. So this is another important problem. We will solve it. The question is, a thin flexible wire of length L is connected to two adjacent fixed points and carries a current I in the clockwise direction, as shown in the figure. When the system is put in uniform magnetic field of strength B going into the plane of the paper, the wires the wire takes the form of a circle like this. So you have to find out the tension in the wire. So that's the question. We can just give a thought. I'll just give you 1 minute to think, and we may discuss after that. So let us just read once again. A thin flexible wire of length L is connected. So this is the whole length of the wire is L actually, and two fixed adjacent point, the wire is connected. Now it carries a current. So this wire is carrying current in the clockwise direction. In this, now when the system is put in a uniform magnetic field like this, you can see here of field strength B going into the plane of the paper. This cross sign indicates that the magnetic field is directing into the plane of the paper. Now you have to find out the tension in the string if the shape of this becomes circle. Okay, then you have to find out the tension in the wire. Okay, so look here, magnetic field is in the direction perpendicular to the plane of the paper, and see there is this arrow. This is the direction of the current through the loop, so it is in the clockwise direction as you see. So in this case actually force will be always, as we have seen, force will be always acting radially outward like this, as you can see, and that's how the wire will be stretched. And it forms a circle. But one thing more you need to remember, so you need to think that if the wire is pulled by such forces continuously, this will be again deformed, or there is a limit to this wire itself. So there must be some forces which are actually, there will be tension in the string, sorry, this wire. So you have to find out what is that tension which is balancing this outward force after certain radius of this uh, circle. Okay, such that the force, these are actually magnetic forces which will be radially outward. Magnetic forces. So you have to find out excuse me the tension. Actually I just need to drink some water. I'll be back in 30 seconds. Yes, so we have to find out the tension. So to calculate the tension, we have to draw a figure, say this one. I hope you are able to see. I'm just taking, this is a zoomed version uh, of a particular portion of this circular path. If I take a just small portion of the circular arc or circular path, this is a small arc. Okay, and see the current is flowing in this direction like this. Okay, so you know the tension will be along this direction. There will be tension along this. Okay, tension along this. If I consider this point and this point, like up to this particular arc, this small portion of the arc between these 2 points. So this is the magnetic force as I have shown here, radially outward, and say this particular angle is theta, which is very small, very small angle, theta. Okay, so this angle is very small angle, and if these angles are this, so this also will be small angle theta. Now the tension is along this way, that means it can be broken into two components, one along this direction, another along this direction, this. Okay, so cos theta components, if you look, the cos theta component here, it will be t cos theta here, and for this particular point this way it is t cos theta. So this cos theta will be cancelling each other, but the sin theta components, they will add to cancel or just balance this magnetic force. So we can write in fact 2t sin theta, which is equal to Fm magnetic force. I I see I here, suppose this length is L, suppose, sorry, this the whole length is L, so this has some dl length, I dl, and the magnetic field is given as B, suppose, so this is B. Okay, so I dl B, and this is, see, in this case I dl and B, dl and B, there will be perpendicular, so I dl, I dl. Okay, so this is the thing. Now what is this dl we can put, and what is this theta? Since this is very small angle, we can write uh, this sine theta nearly equal to theta, nearly equal to theta. So in that I'll write I B, let it be there. What is dl? Dl means this is r, and this is actually theta. So 2 into 2 into r theta into B. Okay, there is let me tell you, this theta is actually, theta is r d theta, sorry, dl is r d theta. So actually this part is portion of, like, half portion of the dl, this part is half portion of the dl, so 2 you will get actually 2r theta, this is, or else let us go with some other way. So this is actually, yeah, this is all right, this is no problem at all so far. And now we can just go with this. Now we have to introduce the length L. So this L has to be brought, and R has to be replaced by L. Okay, so in this case, look, the total length is L is equal to 2 pi r, 2 pi r. So R will be L by 2 pi. Okay, this is what we can write. So then this 2 gets cancelled. So T is equal to I B, R means L by 2 pi. So this will be I B L by 2 pi. Okay, so the answer for this question will be the option C. I hope it is clear to you. I'll just quickly repeat what I have done. So there is a loop like this, you can see, not loop, there is a, so this wire has a length L, and the two ends are connected to some 2 points, fixed points, and this is kept in a uniform magnetic field, so it will experience outward direction, it will experience magnetic force. Okay, that magnetic force will actually try to expand it and make it a circle, but at the same time there will be tension in the wire, otherwise it would have been deformed again. Look how. So suppose the tension is acting like this. This is a part of circle. Okay, this is a part of circle. Suppose the tension is acting this way, so this angle is theta. So there will be two components I can break. One is along this radially inward. Another one is t cos theta tangential to this point. Okay, now see, radially inward forces will actually add to give you magnetic field. Sorry, magnetic force. So that's why I have written magnetic force is equal to 2t sine theta. Okay, sine theta is theta, nearly equal to, and the force, magnetic force ILB. So I have used those concept, ideal cross B in case of cross. Okay, so this is the answer then. We have got IBL by 2 pi. Now we have a problem, this one. See, this is a graphical problem. You have to just choose the answer. You don't need to write any numerical or do any numerical calculations. I'll write the question right before the figure. Which of the following patterns? Which of the following which of the following patterns gives okay, let me, which of the following patterns given in the figure in the figure is valid for both electric and magnetic field? Magnetic field. So these, among these, which one? See, this is for a positive charge particle because it is moving outward. This is for negative charge particle. This is for coming inward. Okay, and see, there are two things, this and this. The second thing is actually seen in case of solenoid. Okay, in case of solenoid, this pattern is being seen. So this is only for magnetic field. This is only for, these two are only for electric field. This is only for magnetic field. What about here? So this is actually concentric circles. This is the only option which is common for both electric and magnetic field. So this spiral, sorry, it's not spiral, it is a concentric circle. This will be correct answer for this problem. Okay, so we move here. this problem, let us first write the problem, or I'll write the problem just above this figure. And infinitely long, I'll just write down here maybe. An infinitely long, an infinitely long hollow an infinitely long hollow conducting cylinder conducting cylinder with inner radius with inner radius r by 2 and outer radius r carries a uniform current density. I'm not writing that, I'm just writing this information. So that carrying, okay, let me draw this figure itself. So there are two radius, that means a hollow cylinder like this. Okay, so this has radius r by 2 and the outer radius is r. Okay, so this cylinder is actually carrying a current, uniform current density along its length. Along its length means like this. Okay, now the magnitude of the magnetic field B as a function of radial distance from its axis is best presented by the figures given. So the magnetic field starting all the way from its center to any point outside and inside. See, this is a point here, there is material, here this is empty. So whether the magnetic field, what is the variation of the magnetic field with the radial distance, that you have to find out. That means what? You have to actually find out magnetic field the between the inner and outer radius, that region. You have to find out inside the core region. So see, we have to actually see the magnetic field, how magnetic field is varying with distance at various places like B below R by 2, because it is radius of this is R by 2. Magnetic field below, so one case should be this. Another case, you have to find out magnetic field B in between. See, in between, so here also you can write 0 to R by 2. Here R by 2 to R by 2 to R. Okay, here up to here. Now outside the, so B, when R is much greater than R. So these are the conditions. In these places, if you can find out the magnetic field, then you will be able to see the variations of the magnetic field with radius. So first of all, let us try to understand which law should be used here. So there are laws like Biot-Savart law to calculate magnetic field, Ampere circuital law to calculate magnetic field. So we will be here using Ampere circuital law only. So let us go to next page. So the magnetic field between 0 and r by 2. What is the magnetic field in this region? Okay, first of all, let us write the magnetic field itself. So magnetic field will be B dot dl. So this should be mu 0 by I or mu by I. Okay, and this I has to be so this is this current, actually the current inside that region, okay, or through this region. So B, we know B is constant, so we can just simply write B L dl must be here, and mu 0, this I enclosed I can write, or passing through the wire. So that we have to find out, and here anyway this will be actually 2 pi and radius small r is r. So B will be actually mu 0 2 pi small r. Now what is this I enclosed? What is the current? See, in case of this kind of cylindrical wire, generally this happens in case of cables. So the magnetic field will be, see, current will not be there in this region. Okay, so magnetic field below r by 2. Then again, magnetic field in between r by 2 and r can be obtained magnetic field in the region small r. So in this region, magnetic field, see, the induced current would be pi per square minus pi into sigma. Sigma is current per unit length. Now if we further put in the limit of integration, so we can find out that this is actually will become some, okay, magnetic field in this region will be, suppose some alpha beta r minus gamma by r. So this will be the magnetic field. So magnetic field variation in this case will be dominated by 1 by r term. So you can see magnetic field has two variations. One is like this also. These two variations are there, we can see. And when r much greater than r outside the wire, the magnetic field will be like not equal to proportional to 1 by r. Okay, so this is how you have to actually either remember or solve the problem to remember the value of the magnetic field at various region, and then try to see the solve. Now given graphs are, yes, these are the graphs. So which one will be the correct answer? We have to see the variation. See, inside there will be two variations that we have agreed. One is 1 by r and another one is, so if we draw it, how does this look? So the drawing part, see, we can see this part is fine. In this case also fine. So r by r2 in this region, so in between region there are two things, so 1 by r and that one, r proportionality constant. So these two things are important. Okay, so let us finalize the answer for this option. We have known the option option D will be the correct answer. Why is it so? We have seen that in three regions, for this case, the current is zero, so magnetic field is zero actually. So this is zero, so that's why below r by 2 or below the like inner radius, inside the inner radius there will be no uh, so no current, and so no magnetic field here. It is magnetic field zero here. Now in between the region we have seen there are two variations. One is directly proportional to r and another one is directly inversely proportional to r. See, when it is directly proportional, we can go like this, but it has 1 by r variation, so it goes very slowly. Okay, so that's why the graph is this. So D, option D will be the correct answer for this question. Okay, so today we'll stop it here. We'll again meet with 12th class problem on Wednesday. Tomorrow we'll again catch up another chapter from 11th standard. So bye for today.